So, next we will be talking about exceptions in ARM. Now, in as far as exceptions are concerned, so we can have the situations which are not occurring in the normal execution of programs. So, when the programs are executed like computations and all that, they are not occurring, but these are some extraordinary conditions. Okay. So, in 80 while discussing about 8085 and 8051, we have talked about interrupts. So, this is basically same as those exception that we call here. So, they are all exceptional situations. So, they can occur from various different situations, like one is that through execution of instructions. So, some instruction is executed and as a result exception has occurred, like the software interrupts. So, we have got this SWI instruction, or for Intel family of processors we have got 8085 we have got RST instruction, 8086 there is another instruction called INT. So, those instructions, so they are called software interrupts, and when they occur some special OS service has to be invoked. So, the processor needs to switch from user mode of operation to some privileged mode, so that this operating system routines will be running in that mode. So, this is the software interrupt. So, this is one source. Another source is undefined instructions, like when the processor is fetching instructions and executing them. So, if it happens like that the opcode part of the instruction that the processor has got does not match with any of the known opcodes of the processor or the coprocessor. Okay. So, coprocessor means that many a times we have got some additional processor that helps in executing programs, like we can have some additional processor which will be doing the say the floating point operation. So, whenever that floating point operations are found, so the task is given to the coprocessor. So, we will see those later. So, this undefined instruction means they are the instruction opcode that it has got is neither the opcode of the processor nor the opcode of any of the coprocessors that it may have. So, that is one condition. Another condition is memory abort, like memory abort means it is trying to get the content from memory, but say the memory location is not available. So, this happens that in the system, though I have got say 32-bit address bus. So, I may not have that much of memory available in the system. So, as a result when it goes beyond that limit, so it is there will be memory fault. There can be side effect of instruction like data fetch failure, like if we are trying to fetch some data. So, when one of the operand is the memory operand, we are trying to get the data from the memory location, and that memory location is not within the address space of the processor, or the particular memory address is absent, the memory chip is not there. So, this type of situation there is a data fetch failure. Other sources which are actually the interrupt sources, like the reset button that we have, the reset pin that we have in the ARM processor, or the FIQ pin, IRQ pin. So, if we are activating those pins, there will be interrupts, and as a result, so these are the other sources for this exception. So, for all these exceptions, so that it happens like this, the processor switches to privileged mode. So, from user mode, so it will go to the privileged mode, either it will go to system mode, or it will go to say one of these FIQ mode, IRQ mode, like that. So, here there are 6 different modes that we have seen previously. So, it will go to one of the privileged mode. Current value of PC plus 4 will be saved in the link register. So, current value of PC plus 4, that is the next instruction. Every instruction is 4 byte long. So, so it will the next instruction address will be saved in the link register. Then the CPSR register value will be copied into SPSR of that privileged mode. So, there are several SPSR registers, one for each mode of operation. So, this CPSR value will be copied onto SPSR register. The IRQ interrupts will be disabled. Okay. So, and if the exception is caused by FIQ, then the FIQ interrupts are also disabled. So, you need to enable the interrupts separately in the interrupt service routine to start to make those interrupts again usable. And the program counter will be loaded with some exception vector address. So, in case of ARM, all interrupts are vectored interrupts. So, their addresses are fixed, they are defined by the hardware. The target address where it will the ISR address is fixed. So, the processor with the program counter will get that value, and the exception execution will start. So, this is the sequence of operations that occur when we are having exceptions in the ARM processor. So, next we see that the vector table. So, as I said that all these exceptions they are vectored interrupt, they are vectored. So, this reset the mode it switches is to supervisor mode and the program counter value becomes all 0. So, that is it comes to the very first location of the memory. So, from that location we can have the OS code for loading the essential portions of the operating system from secondary storage to the main memory. So, that is the reset mode. Then there is one undefined instruction mode. So, undefined instruction exception, if that occurs then it branches to the address 004. Okay. So, it goes to the address 4. So, you see that between two such modes, so we have got only 4 bytes. So, you can have only one instruction in the vector location, and unlike other processors like 8051 or 8085. So, where we have got at least 4 to 8 bytes available, so that the small interrupt service routines can be held there itself. But in general, so that is found to be non-working solution. So, most of the interrupt service routines that we have are more than 8 bytes. So, there is no point putting those only putting only 8 bytes or so in the between two interrupt addresses, vector addresses. So, in case of ARM, so that has been discontinued, and then what happens is that you have in this 4 bytes. So, you can put a 4 words. So, you can put a 4 bytes or 1 word. So, you can put a jump instruction only. So, that jump instruction will take you to the actual interrupt service routine. Then after undefined instruction we have got the software interrupts SWI, and the mode is supervisor mode and the vector address is 8. So, all the software interrupts. So, you remember there are 2 power 24 software interrupts that can occur in ARM processor, and for all of them the control will be coming to this particular address 8. So, from here we should go to the SWI service, and there I should analyze the value of n to figure out which interrupt has really occurred. So, that the whole instruction is available in the instruction register. So, from there it can we can figure out like which instruction which service has been asked for. Then there can be prefetch abort. So, during instruction fetch if there is an abort. So, the operation mode is abort mode, vector address is C, and in case of data abort, that is it is trying to access the data and it is not getting it. So, data abort. So, in that case the address is 10, and then IRQ interrupt has got this address 18, and FIQ or first interrupt it has got the address 1C. So, this is the distribution, and we will see that this distribution it also helps the operation of this processor in some sense. So, first of all this vector location 14 is missing. So, if you look into this, so after 10 the next address should have been 14, but that is not there. So, so that is 14 is missing, and it is for a backward compatibility. So, with some previous version of ARM. So, if we want to for keeping the compatibility 14 is missing. Another interesting thing to note is that you see we have got this FIQ interrupt which is at location 1C, and after that there is no other entry for the vector table. So, what happens is you can start this interrupt service routine from this address directly. So, from 1C onwards, so you can start writing the FIQ service routine. So, that will not override any other service interrupt services, whereas if you for other cases for other interrupts. So, for say just this software interrupt or undefined instruction like that. So, those ISRs, so if they start at this address, so they will override these locations of this vector table. So, as a result the other interrupts will not work properly, other exceptions will not work properly. But for FIQ, this is the last entry, and there is nothing after this. So, we can start this interrupt service routine from that address onwards. So, this saves time, because otherwise other instructions. So, other exceptions what we have to do is put a jump instruction. So, every ISR code in those for those exceptions, so they have got an overhead of one extra jump instruction. So, that way it will take some more time for activation compared to the FIQ interrupts. So, we can see that the FIQ interrupts are faster in ARM processor because of because of two reasons. One reason is that we can have this thing, your interrupt service through this ISR at the exception address is the last one. So, 00 that 1C. So, this FIQ interrupt is faster because of two reasons. One reason is that we have seen that they have got a separate set of registers. So, separate register set. So, that is one reason. Okay. And another reason that we have now is due to this highest address. So, that jump instruction not needed at the beginning of the ISR. So, because of that the FIQ is faster than other interrupts. So, this helps in the operation, like, so we can have the critical interrupts put into this we can have critical interrupts put into this ARM into this FIQ, so that we can get that service fast. Next, we look into one program. This is an example program for finding the maximum of a set of numbers. So, it is so we first the R1. So, it will R1 register, we first clear it, so that it will hold the largest number in it. So, you XOR R1 with R1 and the result is also R1. So, it will be there. So, R2 register. So, I assume that the numbers are stored in an array, and R0 register points to the beginning of that block. Okay. So, it is assumed that the R0 register is holding the, if this is the memory where these values are there, then the R0 register is pointing to the beginning, and this block is ending with a this R2 register. So, this and R2 register is holding the count, like how many numbers are there in that array. Okay. Then we first we compare R2 with 0. So, if R2 is 0, that means nothing to be done. So, it will be over. So, branch on equal to over. Otherwise, it comes to this statement, and in this statement it is LDR R3 within bracket R0. So, the first number that you have is loaded into the R3 register. Then we compare R3 with R1. Okay. So, R1 is holding the current maximum. So, we compare R3 with R1. So, it is assumed that all the numbers are positive. If there are negative numbers, then of course, this algorithm may not work. So, it is you compare R3 with R1, and if it is carry is there, that means if R1 is bigger, then there will be a carry. So, we will be coming to this loop test. So, otherwise this new number R1 is the new number R3 is bigger. So, we move R3 to R1, okay. And then after that, so now I should go to the next next number, and since these individual numbers are 32-bit numbers. So, it is assumed. So, this R0 should be incremented by 4. So, that we come to the next number. So, increment pointer R0. Then we reduce this R2 by 1. So, we reduce R2 by 1, and if it is not same, so branch on not equal to loop. So, if they are if this we subtract R2 1 from R2 and store the number in R2, and then if it is not equal, that is if the 0 flag is set, then this equality flag will be there. So, if branch on not equal to loop. So, we will come back to this point, again load the next number and compare. So, there can be different ways by which this program can be written, and the objective is also not to say that okay, we have done very good survey of this all the instructions of ARM, but we are trying to look into the features of ARM and the types of instructions that are there. Okay. So, this program is just an example on how to use those instructions for doing some operation. So, next we will look into another program. So, we want to compare two null terminated strings. So, null terminated string means I have got so if the first string is say ABC, if the first string is say ABC. So, they are stored in successive locations ABC followed by a 0, this characters A, character B and character C, and then the null character. and the other string may be some x, y, z, w like that, and then 0. So, this is the other string. Now, while we have this type of thing, this is 0. So, we want to compare. So, LDR B R3 R0. So, it is assumed that R0 points to the beginning of first string. So, if this is my memory and maybe in this region I have got the first string. So, this is pointed to by R0, and in this region we have got the second string which is pointed to by R1. So, we get so LDR B R3 within bracket R0. So, it will get the next character from string 1, and LDR B R4 within bracket R1. So, it will get the next character of string 2 into R4. We compare R3 with R4. So, if they are not equal, then naturally they are not same. We just check whether the strings are same or not. So, if they are not same, then we come to this not same location and set this we set this R2 to -1. We set this R2 to -1 to say that they are not matching. If it is so, if they are same, if the first two characters both of them happens to be say A, then we compare with the next character. So, for that purpose R0 is incremented by 1, R1 is also incremented by 1. They are now pointing to the next two characters of the strings, and then we again compare, then we branch to, so BAL is branch always. So, it comes to this loop, and it will again be moving the next character into R3 and next character of second string onto R4, compare them. So, if any of those characters are not same, then this BNE not same, this will be true. So, it will come here and R2 will be getting -1. And if R2 is, if any point of time we find that the strings are not same, we do not compare the remaining characters. So, we just go to this just skip over this same part, and we come to branch always over. So, if R2 is getting -1, so after that we are coming to this point, the program ends. Or if it is always same, then we move this move R2 comma has 0. So, the R2 register gets the 0 value. So, if the strings are same, then with R2 will get a 0. If strings are not same, then R2 will get a -1. So, this is a comparison of this program will just compare between two strings whether they are same or not. So, you can extend this program for to check whether the strings are whether the strings, one string is greater than the other and all that. So, those types of checks can be incorporated. So, next we will next we will look into the advanced processors of ARM. Like as I said that now ARM processors, so they have been developed into the Cortex family of processors, and this ARM Cortex, so it is divided into three different families. Okay. So, one is the A family, Cortex A family. So, these are for the servers, or you can say it is for the application processors. So, for supporting the new operating systems and all that. So, this is for basically computational jobs. If you are there, lots of computations, the server type of application. So, there this Cortex A series of processors are used. Then for embedded processors and real time application, signal processing and control application, we have got our Cortex R series of processors. And for microcontroller oriented applications and processors, so we have got this Cortex M series. So, this for microcontroller and system on chip type of applications. So, this Cortex M series of processors are advocated. So, for our discussion, so Cortex M processors, so they are more they are close to our discussion. So, we will look into those Cortex M processor. So, Cortex M processor, so the register set is same, that R0 to R15 as we have, then the PSR, program status register, CPSR, SPSR is there. The good since it is difficult to learn the complete assembly level programming of Cortex M. So, what they have done, so they have developed very good compiler, C compiler. So, you can write your specification in the C language, and then through this compiler, so you can generate the code for this Cortex the processor, Cortex processor. Then stack based exception model. So, whenever some exception occurs, then these values are saved into stack. So, automatically these register values will be saved, and there are only two processor modes. One is the user mode and another is thread mode, that thread mode or user mode. So, where it will be user task will be executed, and the handler mode for OS tasks and exceptions. So, there are instead of that 6 modes. So, we have got only 2 modes, and vector table will contain the addresses for those exceptions. So, in Cortex M3, so we have got this non-privileged mode or the user mode, and privileged mode or the OS mode. Then this so in the non-privileged mode, this application code will be running, and and in the privileged mode we will have the system call. So, when application code is running, sometimes we make a system call. So, it will go to the privileged mode, or if it is undefined instruction, so it will go to the privileged mode. So, all the aborts, interrupts and resets, so they are all handled in the privileged mode of operation. Okay. So, this is the supervisor or handler mode, and this is the user or thread mode. For interrupt handling, so this has it has incorporated one special thing, like we have got one non-maskable interrupt. So, that so this is this NMI int NMI. So, this is one non-maskable interrupt that is supported, and then we have got 240 prioritizable interrupts. So, 1 to 240 prioritizable interrupts are supported, and these interrupts can be masked. Okay. So, unlike say your 8085 or say 8051, where we have got a limited number of interrupts. So, here the number of interrupts are really large, and this is useful, like if you are having some embedded application, then there may be different devices connected to the system, and also so you may need to have all these interrupts. So, there are 240 such prioritizable interrupts. So, we can have these interrupts can be masked also, and the implementation option selects the number of interrupts supported. So, the original ARM code will tell that it will support up to 240 maskable interrupts, but you can tell that in my system I do not want so many, I want only say 20 of them. So, naturally this NVIC module, that is not nested vectored interrupt controller NVIC module. So, this is a part of this Cortex M3 processor now. So, you can simplify the design of this NVIC. If the number of interrupts are less, then the NVIC design will also be simpler. And interrupt inputs are active high, all are active high interrupts going to the NVIC. So, this interrupt controller has been added in the M3 processor. As far as the exceptions are concerned, so reset is there. So, that is power on or system reset. Then the NMI non-maskable interrupt. So, this is they cannot be stopped or preempted by exception, any exception other than reset. So, that int NMI line is there, by on which you can connect some non-maskable interrupt. Then the faults, we can have hard fault, we can have memory manage, we can have bus fault or usage fault. So, this is these are the different types of faults that are there, that is recognized by the processor. So, default fault or any fault unable to be to activate. So, so we cannot operate, handle that fault. So, they are called hard faults. Then memory management. So, memory processor, they send some violation, the memory access there is some violation. Bus fault is prefetch and memory access violation, and usage fault undefined instruction divide by 0. So, while executing the instruction some exceptional condition occurs. So, divide by 0, the divisor becomes 0. So, as a result the division is undefined. Then there is supervisory call, SV call. So, these are the OS requests. So, we have got that SWI instruction. So, they are mapped onto SV calls here. Then there is a debug monitor. So, that will be handling this, you can monitor the operation of the chip. So, and through a debugger you can just check the values of those. Then there is pending supervisory calls like pend SV. So, this will give you the pending supervisory call. Then there is a SysTick interrupt. So, SysTick interrupt is for internal system timer. So, this is useful, like if you are willing to implement some software some timer in your program. So, you do not need to do anything else, you just use this SysTick interrupt from the M3 processor directly, and there are external interrupts, all those 240 interrupts that we have. So, all of them can be utilized. So, another very interesting feature that this ARM processor Cortex M3 has is the conditional execution. So, it is the if then else type of instruction. So, if then instruction added, so it has there is a 16-bit instruction, up to 3 additional then or else conditions can be specified. Like, say, let us look into this statement. So, this statement, it says that, so uh, int, so this is if then, so we read it like this, if then else then eq. That means, the first instruction 1 will be executed if the condition is true. So, if so then, so this then corresponds to the first instruction, then the next then also corresponds to the second instruction. So, second instruction will also be executed if that condition equality was true at this point. This instruction 3 will be executed if the condition was false, that is the else part, and the last instruction will be executed again if the condition was true. So, in this way you can have up to 4 if then else instructions. So, basically if if the basic instruction is like move, add, sub and or, then this eq, since if the first, second and fourth instruction they were then part, true part. So, for them we have got the qualifier eq, and for the third instruction, so this was else e part. So, it is not of eq. So, that is any. So, instead of so this is similar to this block. So, we do not need to talk about in a single statement. So, I can tell all these flags, and then for the remaining instructions, so I need not tell it explicitly whether it is eq or the flag conditions, the conditional execution flags need not be told separately. So, this helps in writing programs with the if then else type of constructs. So, any normal ARM condition code can be used, and 16-bit instructions in block do not affect condition code flags. So, they will not affect the condition code apart from the comparison instruction. 32-bit instructions may affect condition flags. So, that is the ARM instructions, so they will affect the condition flag. The current if then status is stored in the CPSR register. So, conditional block may be safely interrupted and returned to, and must not branch into or out of the if then block. So, that is there. So, you cannot take a branch instruction from here before completing this if then else. So, you cannot have the third instruction as a branch out instruction, or you cannot just branch into a block. So, you cannot say that I will come to the jump onto the middle of this block. So, that is also not possible. So, those are there. So, this way this M3 processor, so it has got many interesting features, and they are many more features are there. So, I would suggest that you look into this ARM manual for their details, but whatever we do. So, that is actually the ARM processor is one of the very powerful processors, and it has got the advantage because we have got low power consumption, and it is quite powerful in the sense that it is comparable with many of the high speed processors that we have now, with a limited amount of hardware requirement, because you can take only the essential parts and others may not be taken as part of the processor.